Hi everyone, I'm Harichandana from Samsung Research Institute, Bangalore. I will be presenting the paper On-Device Document Classification using multimodal features on behalf of my team consisting of Sugam Garg and Sumit Kumar. Before we get started, consider a simple scenario where you're running late to catch a plane and you're in need of your plane ticket which you downloaded into your mobile a few days back. But now you're not able to find it just because you don't remember the name of the file by which it was saved after download. Isn't this a very unpleasant situation? So, in this paper, we present a solution to this problem which plagues every smartphone user. This shows an overview of the content I'll be presenting in the coming slides. Nowadays, smartphone manufacturers provide users with an ever-increasing storage capacity. But the task of managing these documents is left to the users themselves. Through an internal survey, we found out that every user has almost more than 100 documents stored in their smartphones. And the strategies rely mainly on the name of the file, which is vague after most downloads, as seen in the figure on the right. So, for the first time, we propose a method to automatically categorize documents on device. Since our solution runs completely on device, there won't be any privacy issues as well. But why do we need multimodal features? Categorizing or classifying documents is treated as text classification in literature. Most of these methods rely on the patterns in textual content to determine the class of the document. But we argue that the structural orientation of the text in the document is also an important indicator of the class of the document. What does this actually mean? Let us see through an example. Now, can you try and classify the document based on the OCR extracted text? It would be difficult, right? Now let's see the image of the document. Now I'm sure it will be very easy. Similarly, let's see one more example. Looking at these three images, can you tell me what this image is? I'm sure it would be difficult. Now what if we had a recipe associated with all of them? Then it would be easy, isn't it? Taking this as inspiration, we propose a classifier which uses multimodal features for documents on device, the details of which I'll be presenting in the coming slides. Now, the first challenge which we face is to get the data to model a solution to our problem. Since our task is highly subjective, the classes depend on actual user need. So it is difficult to create a standard data set that suits the need of all. So we create a small in-house data set consisting of 5 classes which can be seen in the table to suit our need. But to actually measure the efficacy and benchmark the performance of our multiple modalities model, we needed a data set which contains multimodal features. So for this, we choose the Food 101 data set, which contains the images and recipes of 101 popular food categories. For text modality, the pipeline is as shown. The input is the recipe from the Food 101 dataset, which is pre-processed using stopwood removal and nematization using the NLTK Porter-Stimmer algorithm. Since the processed data has a sequence length of 100,000 for in some cases, CNN or RNN-based models are infeasible as the computation time is very high. Thus, we use TF-IDF feature vectors, on top of which we train two fully connected layers and a softmax layer. This rendered a model size of nearly 900 MB due to the vocab size. We further observed that TF-IDF vectors are low in rank and sparse. Thus, to solve this, we used truncated SVD, after which we observed a nearly 95% decrease in model size with a mere 1.5 decrease in accuracy. Moving on to the image modality, we use transfer learning to retrain a pre-trained mobile net on our dataset. We use MobileNet as it is optimized for on-device performance. Our image classifier consists of MobileNet, an average pooling layer, two dense layers, and a softmax layer. We freeze the parameters of MobileNet and train only the final layers for first 15 epochs, after which the layers unfrozen is treated as a hyperparameter. We then use batch normalization and dropout to improve our model performance. To combine both the modalities, we make use of late fusion to retain our individual modalities because we might require the outputs of them in some other cases. We use the pre-softmax layer features and merge them to build a classifier. To merge the features, we experimented with different techniques as shown, namely concatenation, average, maximum, and an approach where we train a highway layer on top of concatenation. We observe that concatenation performs the best. The results of our experimentations are shown in this table. You can see concatenation gives the best results. So our final model is as shown. Its size is nearly 13 MB and an accuracy of 89.8%, which is just 1% less than the previous state of art. There is a significant reduction in parameters. We observe a significant improvement in the classification accuracies of food images using the multimodal classifier as compared to the individual classifiers, as shown in this table. For on-device document classification, we first convert PDF documents to a set of images and then use MLKit to extract text from the images. Then we use the same pre-processing techniques as described before. On top of that, to tackle noise due to watermarks, we remove non-English words. We maintain a vocab size of 60,000 and we reduce the rank of TF-IDF vectors to 200 using SVD. We train two dense layers, each of 64 and 32 units each. For image, we use MobileNet and a pooling layer with 512 units and a dense layer of 64 units. We use post-training quantization using TF-Lite to reduce the model size. The total execution time of this pipeline for a single document is observed to be 4.6 seconds, out of which 3.5 seconds are taken by OCR itself. The results of individual modalities and fusion model is as shown. For training fusion classifier, we follow a multi-stage transfer learning approach. The accuracy and loss variation is as presented in the graph. In conclusion, we showcase that multiple modality fusion indeed contributes towards better classification of documents and present a feasible framework to classify documents on device and thus assist users to manage them better on smartphones. Thank you.